With this, a very pleasant evening to our distinguished guest and to each and everyone who has joined us today. On the behalf of SPIE, student chapter of our own Acharya Narendra Dev College, University of Delhi, I, Sakshi Garg, as your host for this stunning event, extend a very warm and hearty welcome to each one of you present here. Just a little housekeeping before we get started. SPIE is an international society for photo-optical instrumentation engineers. The main aim of the SPIE student chapter at ANDC is to promote optics and photonics among undergraduate students. Our chief guest for today is none other than Dr. Gaurav Sharma. Thank you so much, sir, for accepting our invitation.
You're welcome. It's my pleasure to speak at the SPIE student chapter.
Dr. Gaurav Sharma is a professor in the departments of Electrical and Computer Engineering, Computer Science and Biostatics and Computational Biology, and a distinguished researcher in Center of Excellence in Data Science at the Georgian Institute for the Data Science at the University of Rochester. He received the PhD degree in Electrical and Computer Engineering from North Carolina State University, Raleigh, in 1996. From 1993 through 2003, he was with the Xerox Innovation Group in Webster, New York. Most recently, in the position of Principal Scientist and Project Leader. His research interests include data analytics, cyber physical system, signal and image processing, computer vision, and media security, areas in which he has 53 patents and has authored over 220 journals and conference publications. He served as the editor-in-chief for the IEEE transaction on image processing from 2018 through 2020 and for Journal of Electronics Imaging from 2011 through 2015. He is the editor of the Digital Color Imaging Handbook published by CRC Press in 2003. Dr. Sharma is a fellow of the IEEE, a fellow of SPIE, a fellow of the Society for Imaging Science and Technology. In recognition of his research contribution, he received an IEEE Region I Technical Innovation Award in 2018. Dr. Sharma is a 2020 to 2021 Distinguished Lecturer for the IEEE Signal Processing Society and is recipient of the 2021 IST Raymond C. Bowman Award. Now, I would like to invite Dr. Amit Garg, Faculty Advisor of SPIE Student Chapter at ANDC, to welcome our esteemed Chief Guest, Dr. Gaurav Sharma. Over to you, sir.
Thank you, Vita. It's my honor to welcome Dr. Gaurav Sharma to the SPIE Student Chapter, University of Delhi at ANDC. So I don't have words basically to thank you for accepting our invitation to be part of this lecture. As our student has already spoken so much about you, your achievements. I think there is no better person than you to address our chapter students, and all your journey has been filled with so much of innovation. Similarly, that innovation I can very much see in your topic of today's talk. Means it's a very, very unique title. Normally you see very conventional titles, but this is absolutely a unique title, and we are very, very enthusiastic to see this amalgamation of physics and mathematics. And I once again thank you on behalf of the chapter, on behalf of Acharya Narendra Dev College, and I hope your insight is going to motivate a lot of our students to take up their career further in electronics and computer science. So with these words, I you can say
Thank you.
Extend my warm welcome to you, and I'll request you to please start the talk. Thank you so much.
Thank you, Dr. Garg. Thank you, Sakshi, also for the introduction. and Shruti for the invitation. So I will now start sharing. So good afternoon, everyone. It's my pleasure to speak at the SPIE student chapter, and I hope I can make this an engaging talk. So as we go along, I'd like for you to ask questions as I proceed. Please chat your questions to everybody or to Shruti. I will not be able to keep track of both the questions and my presentation, but they will interrupt me and ask the questions on your behalf. Okay. So I think Sakshi already covered my background. I just mentioned that I've worked both in industry and in academia over the years. And yeah, okay. That gives me a perspective from an application perspective on problems, having the industry background. This is where I'm located. When most people think about New York, they think about New York City. New York City is somewhere over here, is where New York City is. We are about 320 miles, 360 miles from New York City in upstate New York. This is the River Genesee, which flows northward into Lake Ontario. And our campus is located over here, roughly. And this is the campus for the University of Rochester. It's a very beautiful...
Sorry to interrupt you, sir. Are you changing the slides?
Yes, I'm changing the slides. You cannot see them?
No, sir.
So let me see if I can share again. So let me do one thing. Sorry. So I guess it might be because of... Can you see the slide now? You see the first slide? You see the change?
Yes, sir.
Okay, all right.
Yes, sir.
Okay, all right. Okay. So this is where I come from in upstate New York, about 360 miles to the northwest of New York City. Our campus is located on the River Genesee, which flows northward into Lake Ontario. This is roughly the spot where our campus is located. It's a very nice classical campus. This is what is referred to as the River Campus. This is what hosts art, science, and engineering. And the university actually has a very substantial medical school, which is located outside of the picture over here. You will not see it. It's just across the street from this campus. And also one of the best schools of music for Western music traditions, which is located downtown Rochester, the Eastman School of Music. Okay. Right. Normally when I'm campus right now, I'm speaking from home, but normally when I'm from campus, I'm in the building over here. That's the computer studies building. Yeah. Okay. This is our main quad, which is where we have the convocation, usually in May, in the open. So that's here. And this is the library building that you're seeing in the background over here. The University of Rochester is a quick background. It's a small private university located in upstate New York. Most people will not have heard about it because it's a fairly small institution, about 4,500 undergraduates across all years. To contrast this with the institution where I did my PhD, North Carolina State University, that has about 10 times as many students across the different years. The university, however, has a strong record of excellence. Among their faculty and alumni, they count at least 12 Nobel laureates, 12 Pulitzer Prize awardees, and 17 Guggenheim Fellows, including some from recent years. Some of the unique features of the university: this was one of the first institute for optics. This is the first optics program in the US, which actually provides a lot of the faculty to other institutions in optics area. So that's particularly relevant to SPIE. I already mentioned the Eastman School of Music, which is one of the top music schools for Western music traditions. And then there's also a highly ranked medical school, which is co-located across the street from us. So with that background, I'll talk a little bit about my research interests. My research interests are quite diverse. Over the years, I've worked across a variety of different problems and still continue to work across a variety of different problems, extending from imaging systems and color science, medical and bioinformatics, multimedia security, and digital imaging and video processing. So in today's talk, I'll be focusing primarily in this area and talking about work in this area, but I will have time after the talk. If you have questions or would like to discuss, we can have a discussion on other topics too. Okay. So the title, as Dr. Garg mentioned, the title for the talk is a little unusual. So I'll maybe sort of justify the title and give you a little bit of motivation for the title. We all live in a world governed by the laws of physics. So you have the proverbial apple falling on Newton's head, leading him to formulate the laws of gravitation. The laws become more powerful when you codify them in mathematical expressions, which allows you to do a variety of things. So ISRO is today routinely launching satellites. So that's something you can do using the knowledge of the laws of physics. But you can also do things which may seem non-intuitive at the first instance, such as this inverted pendulum problem that I'm presenting over here. So the idea here is there's a pendulum mounted on this cart, and unless you do anything else, the pendulum will fall down in this case. But by applying a force here appropriately, you can then balance this such that you keep it from falling. And in that process, the codification of the physical laws in mathematical expressions plays a key role, because that allows you to predict what you need to do in order to prevent this from happening. Okay. So this problem is one where I think the combination of the physics and the math gives a whole that is greater than the sum of the parts. So this class of problems in signal processing, where the combination of physics and maths gives a whole that is greater than the sum of the parts, is the class I'll be talking about in my talk. And that's where the title comes from. So the idea here is the combination gives a whole that is larger than the sum of the parts. It's a play on the words in English. So the examples I will draw from are from what is referred to as imaging. Imaging is what happens in terms of image processing at the interface. So I think we're all familiar with these days with video technology. That's what we're using I'm using to speak with you across a considerable distance. You normally have a scene here. The scene is something which you capture by some system, imaging system, and that gives you a digital representation, which is then communicated in a digital format across, could be fairly large distances, as is the case with this presentation. And then at the other end, you will recreate a rendering of the scene from the electronic data in this case. Okay. So what happens at the interfaces in this conversion from a physical scene to an electronic digital representation, and vice versa over here from an electronic representation to a physical scene, is what you traditionally refer to as imaging. And this is what I'll be talking about, because it's naturally at the confluence between the physical world and the electronic world. It's a rich variety, it's a rich source of physically motivated problems. And I'll be using examples of these from my research over the years. And hopefully also the examples will serve to motivate sort of the students among you and indicate to you how work that you may be doing at this point may have significant impacts later in your career. Okay, so that's something which I'll talk about after the first example that I cover. Right? And as I mentioned already, I'd like you to ask questions as I go along. So if there are questions, please feel free to interrupt and ask. And you'll have to do that through Shruti, in terms of she's the one who has the capability to interrupt me and speak. So the first case study I'll present is from work done quite a while back. And this is however, I still like this study very much because it's a very simple study, and one which illustrates how very simple physics and math principles which you've learned in high school, not even in college, can play a significant role and enable novel research. Okay. So this is the problem of show-through, and I'll introduce what is show-through. Okay. So here's the outline for this part of the case study. I'll talk about show-through and duplex printing. I'll first think about it as an artifact and present a method for analyzing it and correcting it, and then sort of justify the title in terms of why this requires the combination of all three elements: the physics, the mathematical modeling, and the engineering. Okay. And then I'll turn around and talk about how this is an artifact can also be an opportunity, and you can utilize this effectively for a new application. Okay, so that will be the second part of the talk. And then in this case study, and then I'll jump on to another case study after that. So what is show-through? I think most of you, if you're looking at a newspaper in the morning, are familiar with this. The newspaper is not completely opaque. So when you're looking at the newspaper, you can see not only what is printed on the front side, but also a residual image of what is printed on the back side. So this is what is referred to as show-through. When you have a page with printing on both sides, the paper is not opaque, and the printing on the back side shows through. Okay. So here's a cartoon view of this. I'm presenting these two things printed on the two sides, and this is what you get when you scan each of these sides. Okay. Interestingly, this is considered objectionable in electronic scans, even though in the physical world, we tend to completely discount this. So in the physical world, you're seeing this in your newspaper day to day, but nobody objects to this. If, however, you take the scanned images and put them online, then immediately this show through from the backside becomes an objectionable artifact. Here's an example. This work was done while I was at Xerox. And so this is the statement from the Xerox yearbook from that time. This is what was printed on one side. I'll refer to this side as the text side from this. This is what was printed on the back side over here. This is what I'll refer to as the image side. And you can see in both cases, there is show through visible from the other side in this background that you see over here. Okay. Some quick characteristics of show through. It's low contrast compared to the image on the front side. The back side has much lower contrast because paper is not completely transparent either. So while paper is not opaque, it's not completely transparent either. It's more visible in the light regions of the front page. So it's visible in the white regions predominantly over here. It's also visible in these light regions over here that you see over here. Okay. It's blurred in comparison to the printing on the front side because the light has to go through the sheet of paper in order to come back. And it's transposed. That's just the fact that the printing on the back side is going in the other direction compared to the front side. So what would be an image processing solution to this problem? If you're presented with show through of this type, then a simple image processing solution would be to say, wait a minute, this only affects things which are in the light regions. I could make everything which is lighter than this sort of residual image that I see of the United States in the text side, make that white, and that should eliminate most of the show through. Okay. So that is what is referred to as thresholding. You remove show through from black and white text. So you convert regions with reflectance above a given threshold to white. This is showing you the pictorial views. You choose a threshold, convert everything above that reflectance, and make that white. Okay. So this eliminates the show through from black and white text. But for images and grayscale text, it also removes low contrast front side information. And show through is still visible in some regions. Okay. So here is the result from the text side. This looks quite good, as one would expect. I motivated this for the correction for the text side. This is what the image side looks like. Okay. And you can see I've eliminated the show through in the background white regions, but it's actually become more pronounced here in the state of Texas in the United States, where you can see this in the light gray region. And quick thought will indicate to you there is no thresholding solution to this problem. Okay. No matter what threshold you choose, if you choose the threshold to eliminate this show through, you will also eliminate Texas from the map over here, which is not what you want your image processing solution to do. So what I'll talk about is an image processing method for show through removal, which combines the physical modeling of the optics and appropriate image processing and mathematical simplification in order to arrive at a solution. Okay. So you will work with scans from both sides of the duplex printed page, work with an image processing technique to come up with what would be the result from these scans if there was no printing on the back side. Okay. Why do you need the scans from both sides? Using the scans from both sides can help distinguish what is low contrast front side information from what is show through from the back side. And the second part is that it's not just enough to know where there is show through. For instance, if I know there is show through over here, that's not enough. I also need to know what do I need to correct this value to. And the correction is different in different regions. So in these regions, making this white was pretty okay. In this region, making it white for the show through regions would not be the right solution because it would stick the text would still be visible here to just be lighter than the background in this case. Okay. So this is important. I need a model to be able to predict how much is the contribution of show through. So I'll walk through these. Again, this is at the level of high school physics. So hopefully everybody can stay engaged. Okay. So this is a simple model for the scanning process. I model things for the printed paper as 3 layers. There's the sheet of paper, which is characterized by the amount of light it scatters back at you. The large part of the light is scattered back at you because it appears white. Okay. A small fraction of the light actually gets transmitted through. So that's the other part of the paper's property that matter. There's the fraction of light it scatters back and the fraction of light it transmits through. Okay. There's printing on the front side and there's printing on the back side, which I model as a layer of transmittance. There'll be a certain layer of transmittance associated with the printing on the front side. If something is black, there'll be no transmittance. None of the light will be transmitted through. If something is white, all of the light will be transmitted through as far as this layer is concerned. Okay. And if there are things are gray in between, you will have a transmittance somewhere in between the two. Same thing for the printing on the back. I model that also as a layer of transmittance with the same attributes. Black becomes 0, white remains 1, and things in between are intermediate. There's also the backing of the scanner, which also has its own reflectance, and this will be also something which will factor into our analysis over here. Okay. So now in trying to analyze this, I can think about what is the reflectance that my sensor here will see under this setting. Okay. So I can think of two components of light in my simplified model. The first component of light is the one which comes from the lamp. It encounters the front side printing, is scattered back by the sheet of paper. From the sheet of paper, it encounters the front side printing again on the return, and then comes back to my sensor. The reflectance that this term will contribute will be the transmittance of the front side printing layer, which is what is encountered on the way in, the scattering fraction of the sheet of paper, which is the fraction of light that the paper scatters back, and the transmittance of the front side printing again on the return. So the front side transmittance twice multiplied by the scattering fraction. So that's this term over here, the product of this term. Okay, so maybe I should explain my equations here. The RF stands for R stands for reflectance, F stands for the front side, S stands in the scan, XY is pixel position. This is the transmittance squared at that position for the front side layer, multiplied by the scattering fraction for the paper. That is the first term I talked about. That term I've justified in my description. The second term I can similarly look is the term which corresponds to the light which goes all the way through, comes back all the way through. So it will encounter the front side printing twice, once on the way in, once on the way back. It will encounter the transmittance rather than the reflectance, rather than the scattering fraction of this duplex printed sheet. It will encounter the backside printing twice, once the way going in, once the way coming back. It will encounter the reflectance of the backing once. Okay. So that simple physical model. The second term is this transmittance of the front side squared, transmittance of the paper squared, because it's also twice on the way in, way out, reflectance of the backing, and transmittance of the back squared. Okay. So this is the reflectance that your sensor is seeing in the scanning process when you do the front side scan. And the fact that even though you're scanning the front side, and this reflectance depends upon the printing on the backside, the transmittance of the backside layer is reflecting the dependence on show through. I have a similar equation for the backside scan. All that will happen is the front and the back will interchange. F and B will interchange positions, but the equation is otherwise exactly the same. Okay. Now, mathematically, you can start thinking about this problem. You've got two equations and two unknowns. You want to figure out what is printed on the front side, what is printed on the back side, roughly speaking. So you maybe want to figure out what is TF square and TB square. So you can think about trying to solve these two equations and two unknowns. There are also two problems with these equations. These are nonlinear equations, but that's not the major problem. The bigger problem is that this model is a little too simple. Our interaction we've assumed does not have any kind of spatial interaction. We assume that each pixel only influences that region. In reality, light as it goes through the sheet of paper undergoes spreading. So you cannot really model this as a pointwise interaction. So I'll handle each of these two problems in turn. First, I'll address the nonlinearity, and then I'll address the interaction not being pointwise. To address the issue of the problem being nonlinear, I will do a linearization of the problem. This is, again, very simple high school math. Everybody has done Taylor series in the courses on calculus. So let me first present the equation, then I'll discuss how the connection with the Taylor series comes about. So I look at the density of the front side scan. So optical density, which is something most of you in SPIE should hopefully be familiar with, is the negative logarithm of normalized reflectance. So I take the reflectance that I saw in the scan, divide that by the reflectance of the white paper. So this is paper which is not printed on either side. Okay, that will be the largest possible value. If I go back to this equation, if there's no printing on either side, there's no printing on the front side, this quantity is 1. There's no printing on the back side, this quantity is 1. So the reflectance of white paper which has no printing on either side is simply SP plus TP square RBK. That's the term you're seeing in the denominator over here. Okay, and that's the highest reflectance I can have. So I normalize this with respect to highest reflectance. This quantity always is going to be less than 1. I take the logarithm of something less than 1, that's going to be negative. I stick a negative sign in front of that, I'll have something positive. This is what is referred to as optical density. Okay. So I convert to optical density, and if I play around with the equations a little bit, you can see that I can write this as this is the density I would have if there was no printing on the backside. If TB square was 1 minus this term. Okay. Let's look at this term over here from a physical perspective. The transmittance of the paper compared to the fraction of light that the paper scatters back is quite small. Both are values between 0 and 1, and the transmittance is quite small. That's why paper mostly is opaque. When you're holding a sheet of paper, you maybe see your residual images, what is on the backside, but you don't see primarily what is on the backside. Okay. So this quantity, RBK, is between 0 and 1. This denominator is much larger than the numerator. Okay. This quantity, 1 minus TB square, is 1 minus transmittance square. Again, it's going to be between 0 and 1. Okay. So this entire term that I have over here, which I'm showing with my mouse, which hopefully you can see, is a small term compared to 1. This is where the mathematical approximation comes in. I use the Taylor series approximation. For small x, the natural logarithm of 1 minus x is approximately minus x, based on the physical insight that we have, which is that paper scatters most of the light back at you. Okay. So this gives me this equation where I can use the Taylor series approximation, and I now got a linear relation. The density that I have in the front side scan is the density I would have in the absence of printing on the back side, plus a small fraction of the backside absorbance. This 1 minus TB square, I'm just calling the backside absorbance. Okay. Just to visualize this, these two are different transformations. This is a negative logarithm. That's what is shown over here. So I'm transforming the data in this manner. And this absorbance is just 1 minus a certain quantity between 0 and 1. So it will map 0 to 1 and 1 to 0. So it's flipping this. Okay. This is an equation which really requires the combination of the physics and the math in order to arrive at. Okay. So now the second problem I mentioned is that the model was too simple. In reality, the interaction is not just point-wise, but also involves the neighborhood. Okay. So to address that, rather than use this simple model over here, I'll replace this term by a point spread function. So this is just representing how much the light is spreading as it goes back and forth through the sheet of paper. This is what I call the show-through point spread function. So rather than modeling this as a simple scalar multiple, I model this as this point spread function convolved with this. So this you can think of as how the light is spreading as it goes back and forth from the back side to the front side in this process. Okay. I'll call this the show-through point spread function. And keep in mind, physically, it's representing this term, which I expect to be small in magnitude at all points. So now if you had some way of knowing this term, hxy, you could simply correct for this equation. This is what you want. You want the front side density or reflectance in the front side, which are two equivalent things, is what you want to compute if there was no printing on the back side. So you could simply take this quantity over here, if you knew these other terms, and subtract this. This you have from the scan for the back side, an approximation to this. This you don't know. So that's the challenge. Also, the alignment between the front and the back side is not something that you know. Okay, so this is unknown. That's a challenge. So this is where the engineering insight and intuition comes in. Most of you these days don't know what a landline is. But before the era of mobile phones, the telephony was something which obtained or operated through landlines. So there were actual physical connections of wires which were building your telephone service to your home, and also allowing you to speak with somebody at long distances by connecting through a variety of exchanges. Okay. So the way this was designed for economic reasons is that there's only two pair of wires between your home and the exchange, the local exchange. These wires carry the information in both directions, what you're speaking and conveying to somebody far away, and what they're saying, which is coming to you over here in this case. Okay. So from the exchange, there were two sets of wires. They're separate wires. There is the wire which is supposed to be, so sorry, I spoke in the wrong direction. This is the signal coming to you from the long distance speaker. This is your speech going to somebody in the other direction. That's what the arrow is indicating. Okay. So technically, when the person here is speaking and you're quiet, you should only hear what they're saying, and the signal should just come to you. It should not go back here. That's designed by this hybrid element over here. In reality, this being an analog element would always be imbalanced, and there would be some element of echo that is going back to the person over here. The speed of light is quite fast. Normally, when you're speaking with somebody terrestrially, this echo comes back so quickly that you don't even notice it differently from your own speech. However, if these are connections are made over geostationary satellites, that introduces a very substantial propagation delay. Okay. So the propagation delay for back and forth going all the way from one end to the other end is about half a second. So you would notice this very objectionable echo in intercontinental phone calls made over geostationary satellite connections, where you would hear yourself speak what you said a substantial time after you, about half a second after you said it. And that's very perceptually annoying. All right. So this was one of the early applications of signal processing and adaptive signal processing in particular. The idea here of solving this problem is that if you look at the signal over here, which is the echo, this is just a delayed and attenuated version of what you have over here. So you can put this circuit over here, which estimates how much to delay this by and how much to attenuate it by. And then that is something you can then cancel from this. And this has been successfully applied in telephony for quite a while. All right. So once you realize this, you realize the problem of show through is exactly the same as the problem of echo in telephony. So how do you tackle it? This is presenting you a graphical view of the algorithm. You have the front side scan image. You convert that to density. That's the transformation over here. That came from the mathematical and physical modeling I presented earlier. When you're presenting a given, processing a given pixel, you will require the backside image for the similar region, for the neighborhood region for this. The backside image region, however, will be in absorbance. So whatever is the reflectance, you do 1 minus the normalized reflectance, and that will give you this backside absorbance over here. In predicting what is the contribution of show through over here, you will use a neighborhood of the corresponding region in the backside. Okay, this will be the support of your adaptive filter, which you're using. And then you will have a set of weights, which you will predict this coefficient and come back and figure out what is the correction. They'll give you the corrected value, and then you can do this from pixel to pixel as you proceed. How do you choose these coefficients for this adaptive filter weights? Well, if you can detect regions in which there is no printing on the front or the back side, you know, or sorry, if you can detect regions in which there is only printing on the back side and no printing on the front side, you know that in those regions, the corrected value should be white. White means that this should be the same as the denominator. If the corrected value should be white, this should be the same as the denominator. So this desired value over here, the numerator and denominator match, logarithm of 1 is 0. So the desired value is 0. Okay. And that allows you to estimate what this point spread function should be in this case. This is called front side silence detection, and you adapt the coefficients according to this. All right. So the algorithm becomes fairly simple adaptation of what was done in echo, cancellation, and telephony to this problem of show through. You have an adaptive filter to estimate and track the show through PSF. The filter is adapted in regions in which you have printing on the back side and no printing on the front side. And the desired output density here is 0. There are a variety of adaptation algorithms. I think some of you may have seen these. If you are in your final year, you may have seen some of the adaptive signal processing algorithms. Or if you're in graduate school, others will see this. I use the simplest one, which is called least mean squared algorithm. Interestingly, this is also the same thing, which is very analogous to stochastic gradient descent, which is being used in large variety of deep learning problems today. A minor detail, we also process the image in a serpentine scan. What is serpentine scan? Rather than go across left to right, one scan line, next scan line, one left to right, we actually go left to right, one scan line, next scan line goes right to left, and so on in this case, and proceeds in this manner. Okay. What that does is maintain spatial contiguity, which is important. Okay. And then I allow a large support for the filter, which also takes into account the misregistration between the front and the backside scans. So I'll skip this in the interest of time. This is just the gradient descent idea and present some results. Okay, so how does this technique work? So much for theory. How much does it work in practice? So this is actual results from a scanned page with text on one side and the image on the other, scanned on a normal desktop scanner. And okay, this is the result from the cancel text side. And you will see the show through has been eliminated from this. You'll also see that I have not thresholded. If I was to threshold the background, this variation in or gradation illumination in the background that you see in the edges over here would have become white. That's not lost. Okay, that's not been done. But this side was easy anyway. This is the image side. And now you'll appreciate that the show through has not only been eliminated from the white background regions, but it has also been eliminated from the light gray regions over here. Okay. All right. Having got the physical insight, you can now go back and ask, how does this, or rather having gotten the solution, you can now ask, how does the solution agree with the physics of the problem? So if things work properly, as I'm done finally, what I expect is my point spread function over here to represent what the spreading of light is doing as it goes through the sheet of paper. So I expect this to be localized about a center of mass and have a distribution about that center of mass. So I can look at my adaptive filter coefficients at different locations, and they should be representing this sort of distribution about a center of mass. And that's what you indeed see. This is the coefficients at this pixel location stated over here. You can see the values are fairly small as compared to 1, which is what I motivated, because from the physical model, these quantities are going to be quite small. And this is roughly distributed about the center of mass over here. As you look at a different pixel location, the picture is similar in sort of its qualitative behavior, but think the center of mass has shifted. What's happening here is that adaptive filter is automatically taking into account and compensating for the registration between the front and the back side. We can also do this experiments on different paper. This is a scan from IEEE Spectrum from around that same time. Magazine paper tends to be thinner. Since magazine paper tends to be thinner, you will have more show through, and it will also be spreading less because there is less traversal through the sheet of paper. Okay. This is the best I could do with thresholding this, and you can see the show through still remains visible over here. You can't really do this. Over here, you also introduce some artifacts from the fact that you're transitioning rapidly from white to this place where you had the threshold. Okay. This is the result with show through correction. And you can see that you eliminate the show through not only in the white region, the light regions, but also in the light gray regions over here. Again, looking at the show through point spread function, because the sheet of paper is thinner, the magnitude here is larger for our filter coefficients, and it's more concentrated in a narrow spatial region because there is less spreading that the light undergoes. Okay. So this is a point I'll sort of pause and give you a little bit of sort of idea of why the title and also where this work came from. Okay. So far I've presented to you the problem of show through in duplex document scanning and presented this as degradation, which you can electronically correct using scans of both sides. It's an effective method of correction that works in both white and light gray areas. If you think about it, all the components that I talked about individually are really simple. The physical model used nothing more than high school physics. The mathematical simplification we did was also just high school math Taylor series. Signal processing that we used is a little bit more sophisticated, but again, something which you'd encounter in your first course in signal processing. However, these are all key components which combined make the whole much greater than the sum of the parts. For students among you, I'll also motivate. Where did I first learn about echo cancellation? So when I was a student at University of Roorkee in my undergraduate, we had a mandatory internship program after completion of the third year. And I went to Space Application Center in Ahmedabad and worked on echo cancellation, implementing an echo canceller on the TMS 32020, which was the DSP chip at that time. Okay. So I had worked on this problem as an undergraduate on my summer internship. I knew echo cancellation from then. So years later, many years later, when I was at Xerox working in the research, and the problem of show-through came up, I could immediately make the connection. Wait a minute, this is the same as the problem of echo. So I should be able to correct this using echo cancellation. So my first approach was to just try and hack it. I just tried to put the signals together in an echo canceller without any of the modeling and the mathematical simplification I presented. It would work in certain regions, but not work in other regions. Then I said, okay, maybe I use some physical intuition, convert both the front and the back side to density. Again, it would work in certain regions, not in other regions. Finally, I drew the simple model that I presented on my board and did the analysis that gave me the insight. The front side image needs to be converted to density. The back side image needs to be converted to absorbance. At that point, all my programming was done. All I had to do was change the way I was transforming the front and the back side images. And things worked from there.
So there are few questions.
Sure.
A student is asking, will it work if the colors of the elements in the duplex paper were not black, rather if they were multicolored?
Yes, they will work if they're multicolored. They'll work on a per channel basis because nothing here is changing the distribution of light from one wavelength to another. So it'll work on a per channel basis. You can apply this to the red, green, and blue channels captured in the scan independently.
Next one is the equation changes according to the quality of paper?
Yes, it changes. So this is something you saw over here. You see that this is the beauty of adaptive signal processing, which I did not talk about in detail. And probably you will appreciate once you have a course on adaptive signal processing. This is thinner paper, so the light spreads less when it goes through the thinner sheet of paper. That's why this is over a narrow region and higher in magnitude compared to what you had over here, which is thicker paper. So it's smaller in magnitude and spread out over a longer region, or a larger region in terms of spatial region.
Okay, sir. You can continue.
All right. Okay. So far what I presented was really this artifact, show through as an artifact. And I presented this simple example in considerable detail, but hopefully you will appreciate this really sort of embodies the title, that the combination of the very simple physical model with simple mathematical simplification resulted in a whole which is much greater than the sum of the parts. In the second part, I'll turn this around and I'll talk about how you can also use this show-through phenomenon as an opportunity and exploit it. So I'll make this part quicker because I know time is short. I want to cover maybe a couple of case studies. So I'll go through these two case studies at a more rapid pace in this case. Okay. So this is the example of case show-through watermarks and advice from my math professor. Okay. All right. So the motivation for this comes from conventional paper watermarks. All of you are familiar with currency. If you look at money, you see there are visual watermarks embedded in the currency. And these are visual patterns embedded in the manufacturing process in which you make the paper pulp thicker and thinner in the manufacturing process to embed this watermark. Mostly they're imperceptible when you're using the information on the front side. And in terms of a technology, this is a very long-lived technology. They've been in use since the late 13th century. They're commonly used today in banknotes, passports, and legal documents. They were also used in ornamentation for high-quality stationery. That's becoming really rare. I don't know if anybody who's used bond paper recently for sending a resume anywhere. That's not something which these days people are doing. A big advantage of this is visual detection. You don't require any specialized equipment. If you have a currency note you need to validate, you can easily validate. So here are examples of US currency for different denomination bills. Euro from bond paper, which is really not something which is most of you would be familiar with. Okay. All right. Now there are, as opposed to these physical watermarks, there are digital watermarks. Majority of these are for electronic content, which are used for copyright protection. So if you're watching a movie in a theater these days, most of the images video will be watermarked, which will be indicating what theater the movie is playing in, what is the showing, and so on. So if you were to take your video camcorder and record this image from there and then distribute it on the internet, they'd be able to figure out which theater this happened from and then start to focus the investigation there. Okay. This requires computer-aided detection. There are a few techniques for hard copy documents, but most of these also require computer-aided detection. I'll not talk about these in detail given the time. Okay. So our example in this idea is, or in this case study, our motivation is to try and mimic conventional watermarks in duplex printed documents. So by the way, this watermarking is still one of the mainline technologies against counterfeiting in the United States. In the United States, these bills are all the same size. So the look and feel of currency is hard to replicate. So you can't replicate the feel of that paper. So a common counterfeiting trick in the United States is people will bleach $5 bills and print $100 bills on those. Okay. And if you look at the precedent that is there in the bill, in the watermark, that is different. So it actually prevents that from happening. And the nice part I already mentioned is that you have visual detection with no additional equipment. Okay. So what's the idea over here? So to give the idea, I'll give you a little bit of background in halftoning. Halftoning is the process by which you see almost all printed images today. So if you're looking at a newspaper, the newspaper images and halftone there. In reality, the image is grayscale. However, the printer is only capable of producing black and white. I apologize, there'll be some artifacts over here because of the scaling that will probably be happening in the process of sending this projection over the internet to you. So this produces the illusion of grayscale on binary printers. And this relies on the fact that your eye acts as a low-pass filter and filters the detail over here. The optimal technologies, choices are technology dependent. I'll again not go into those. But here's an example of, this is, again, if you'll recognize from the earlier image, this is the University of Rochester chapel that I had in my introductory slides from where I'm from. This is showing you the image of that halftone over here. Okay. All right. So these are what are referred to as dispersed dot halftones. This is one type of halftone. For this, people had proposed watermarks, which try and use this simple idea. Is that when you're going to produce this pattern, so if I want to produce a certain gray level over here, I want to produce a distribution of dots which has that fraction of the pixels black and the remaining fraction as white. Okay. So the idea behind halftone correlation watermarks is you design these watermarks such that you will have this two templates, two adjacent regions. In these regions, the dots will be in the same positions in the regions which are in the background. In these regions, the dots will be in what is called as conjugate position. So let's say you want 50% gray. So you want half the pixels to be black and half of them to be white in order to produce the illusion of 50% gray. In this region, those 50% gray black pixels are completely aligned when you shift this by the right amount and overlay in. In this region, they're in the opposite phase. Where you have black, there is white here, and vice versa. When you overlay these, you can see that when you overlay black on top of black, that does not change it. Things remain black. White on top of white remains white. This gives you the same identical pattern. This conjugate pattern, on the other hand, becomes completely black. So you can design this into the halftone. Again, a lot of detail, which I'll be skipping. And then once you've detected this in the image, figure out what is the periodicity with which this tile is occurring and shifted by the appropriate amount and overlaid, you can actually see the watermark. Okay. This is showing you an example of the watermark visualized over here. This is showing you a detection from an actual scan. So this is something which is printed, scanned, and then recovered from there. Okay. A lot of detail I've skipped over here. The scanning, this detection of the scan is quite involved and requires a lot of computation because scanning, the printing process introduces quite a bit of distortion. Things are not completely in the same positions which you asked them to be when you printed them. So you need to compensate for all of that. Okay. So what's a simple idea? A lazy man's invention to address this? Well, why not just print these two things on the two sides of the paper? If you just print them the two sides of paper, and then when you look at the paper, light through the paper, they will get optically overlaid, producing the watermark. Okay. Now, as most lazy man's invention, this also has a problem that it doesn't quite work. when you have this printing on one side, when it goes through the sheet of paper, it doesn't quite remain the same. It goes through some spreading. This is the point spread function I talked about earlier, or related to the point spread function I talked about earlier. Okay. So when you overlay this, you don't quite get the watermark. Right. So how do you address this? Well, the way we address this is that we use a different type of watermarks. These watermarks are what are referred to as clustered dot halftones, which are typically changing not the number of dots, but the size of the dots. So if I want to produce something from light gray to black, rather than changing the number of dots in the given region, you can see I'm growing the size of the dots over here in this case. Okay. And this is what is predominantly used in most of the printing that you encounter in, for instance, the newspaper and books and so on. The other technology is also used in printing and digital printing, but this technology is also quite predominantly used in this case. So what do we do with this? We vary the phase to embed a halftone pattern. Okay. So if you imagine you had these dots centered in these locations, normally, this is what is reference. If I change the phase as I go along the horizontal direction in this manner, the dots move down as I go in this direction and then come back up. If I now overlay the two, you will see these dots are offset on top of each other over here and offset from each other over here. Because these dots are offset from each other over here, this region will be, if I take away the grid, which is just for my conceptual visualization, this region here will be darker because there are more dots. This region will be lighter. So I introduced this halftone watermark pattern, which is light and dark. Okay. This is an example from an image. And I think you may be able to see a little bit of residual here. That's largely to the scaling artifacts. That's not what you see in the actual printed image. This is what you get from overlaying these two. This is done entirely digitally. If you do this in print, this is showing you what you get in print. Normally, if I was giving this example in person, I would have shown you an actual example, which is actually better than this because this was one of the early stage examples. Okay. So I've taken this paper, scanned this in as I would scan a transparency, and you can see this printed pattern of T is visible over here. You can also appreciate that the T is not completely dark, unlike what I showed you in the electronic region. And that's coming from the fact that the registration is changing. So in the first part, I presented show-through as a degradation, presented a method for correcting for show-through. In the second part, I showed you how that can also be used as an opportunity and used as a mechanism for embedding watermarks, which mimic conventional watermarks, which can be detected without any electronic or computational processing. Any questions on this part? All right. So in the last part, I'll talk about some other more recent work. There's work which I'm using will be the primary basis of this, but I'll also talk about much more recent work once I conclude this case study. This is about color barcodes for mobile applications. If you look at emerging barcode applications, most of you have probably seen QR codes today. These were there in my announcement of my talk, for example. This is a very nice way to connect between the physical world to online information. All of you are using these, so I don't really need to belabor this in any way. Okay. Common barcodes were designed to be black and white because they were designed in an era where they were meant to be printed and used on printed interfaces. And the printing was much less expensive for black and white than for color. And also the sensors for these were designed to be specialized sensors which sensed only the black and white. There's an increasing interest in making them color because capture devices, I don't think anybody has a cell phone with a black and white camera. You'd have to pay an arm and a leg to get that. And then if you look at most of these applications where people are doing this, these are related to advertising, outreach, and so on, then the images are already in color to begin with. Okay, except for the barcode. So why not use this color as an opportunity and increasing the encoding rate? Have a smaller barcode to put the same information or increase the amount of information you're doing. You can also use higher robustness and better aesthetics. Okay. So people have worked on this prior to our looking at this problem. A number of people have designed this. The Microsoft color barcodes were actually in use for USA Today for some time before they discontinued the use. Other people have designed these. These designs, if you will see, are completely unrelated to the traditional QR code design and the traditional barcode design. One of the things they're essential to do is that these layers of printing are done separately. You print this printing process prints in layers of cyan, magenta, and yellow, and they can shift between as the press is going from one layer to another, which changes the color, and then the barcode does not work as well in this case. So what's our approach? Again, simplicity is something which is actually quite powerful. Well, we know that printing is at least using 3 layers of cyan, magenta, and yellow in the printing process. Okay, why that is a whole different sort of tutorial, but for the time being, accept the fact that printing is using these layers of different colorants. So rather than embed in colors, we embed in colorants. So it sounds like a play on words, but it's an important play. So instead of trying to change the colors in the output image, what we're doing is we're saying that the printing process is using these 3 channels, cyan, magenta, and yellow. In each channel, we embed a barcode independently. This generalizes common monochrome barcodes to color. Whatever you could do with the monochrome barcode over here, you could use any of those. It provides you 3 times the encoding rate and is robust against interseparation misregistration because this entire channel moves by itself when the printing press undergoes registration. What's the challenge with this is the challenge of color interference. So this is showing you a cartoon view of what would be ideally happening. If you're printing in, so this is showing you a function of wavelength. Roughly, you can think of this as the region from 400 to 700 nanometers is the visible region. And if you divide it into bands of 100 nanometers each, you can think of the region from 400 to 500 nanometers as the region which produces the sensation of blue. 500 to 600 nanometers producing the sensation of green, and 600 to 700 nanometers producing the sensation of red. This is the reflectance shown along this axis. And as you print more and more cyan, you take away more and more of the light in the red region. Things become darker over here. So as I'm increasing cyan, things are going down over here. So this will influence largely the red capture of your channel. Similarly, magenta printing will influence largely the green capture, and the yellow printing will impact largely your blue capture. In reality, things are not so nice. Physics does not behave that well. You actually have interference between the channels, and the end result is that you get interference in your barcode. So this is showing you a print which is printed in 3 stripes, cyan, magenta, and yellow. This is the scan red channel, this is scan green channel, scan blue channel. If things were perfect, this is the image that you would see in this channel. You would not see any of the other 2 images. This is the image you would see in this channel, and this is the image you would see on this channel, not any of the other 2. And you see things are far from perfect. You see quite a bit of interference from the other channels. In particular, look at the yellow. There's a lot of interference from the other channels in the yellow. How bad is this for QR codes? This is from an actual example of a QR code for the cyan, magenta, yellow channels and the corresponding red, green, and blue. Let's focus on this block inside this here. This block is white over here in the yellow channel. Over here, you see it's got printing in the other channel, in the magenta channel, so it's actually magenta. When you scan it, however, this is actually quite dark. And interestingly, it's darker than the outside black square that you have over here. So the secondary signal from interference is stronger than the primary signal. So you cannot do thresholding here either to address this.
So
And what do
there
we
are
do?
few questions.
Sure, please.
What is 4-color printing?
What is 4-color printing? 4-color printing normally does printing using cyan, magenta, yellow, and black. So, so if you think about a display, such as the display on which you're maybe seeing this presentation on your screen, the display starts with the black screen and adds light to produce different colors. Printing is the inverse of that. You start with the white paper and take away parts of light to make it different colors. Okay. So traditionally you print with cyan, magenta, and yellow. Cyan is like taking away red. Magenta is taking away green. Yellow is taking away blue. This is what you need for color printing. In addition, you will also additionally use black because these colorants were traditionally expensive and you wanted to use less of these colorants. Also, using black allows you lesser ink, so it will not flow on the sheet of paper and can produce better blacks. So that is what is 4-color printing. Any other questions?
Okay. So difference between QR code and the other 2 codes shown.
Oh, so these were defined at different times by different standards and different companies. The QR code is the one which is most dominantly used. The Aztec code is used in boarding passes quite frequently. If you see the boarding passes, they're often using the Aztec code. Data matrix is another standard. All of these are standard codes for black and white barcodes, but they're just different standards.
Okay, sir. So which encoding technique is used in Ethernet?
In Ethernet,
Yes, sir.
Ethernet is just a network. It's not tied to any encoding technique. It's not using any encoding technique. It's something you can use any kind of, if you're using a QR code, you can use any kind of encode, any of these over the internet. There is no restriction from this. These are different things. These are orthogonal to each other.
Okay, how sensors detect QR code?
How sensors detect QR codes? Okay, so say we'll first locate these localization patterns, the patterns which are there over here, to figure there's actually a QR code in the image. And then they will detect each module to see whether it's dark or light, which gives you one bit of information for each of the modules, and then correct for errors. So to recover the message. So there's a whole process behind it. And that's partly the beauty of our invention. We are not reinventing all of that. We're just reusing it because we're doing this on a channel basis.
Okay, sir.
Other question? Okay.
No, sir.
Okay. All right. So again, you have the problem of interference, and this is not easy to address. Okay. So how do we address this? So how much time do I have? Should I be aiming to wrap up in the next few minutes?
No, sir, you can continue.
Okay.
No time foundations.
Okay. So then I will maybe elaborate this idea also, and also give you, since there were questions about it, and this is also
Sure,
of
sir.
current relevance. Okay.
Sure.
This interference also depends upon the device you're looking at. In this case, this is showing you a BlackBerry. This is a Motorola. So this is work done a while back. I'll talk about more recent work in this domain also. It will depend upon the printer, the capture device, and the illumination. So you can't necessarily say that, okay, I've learned this once and use this throughout in my processing. So what we do in this case is, again, have a physical model for the print and capture process, where there are model parameters dependent upon the printer, capture device, and the illumination. The relevant model parameters which play a role in the interference is something we will estimate by using machine learning techniques, such as expectation maximizations, or using a pilot signal. And I'll highlight both of these, okay, which then allows us to estimate the interference and actually correct for the interference using these estimated model parameters. So here is, again, since this is a talk for SPIE where people are interested in optics, this is the place where we model it. It's very similar to the model I presented in the earlier part, except that this is now also a function of wavelength. You have some light as a function of wavelength, which is illuminating your printed paper, which has maybe the printed barcode. The reflected light will be the illumination light multiplied by the transmittance square of the yellow layer, transmitted square of the magenta layer, transmitted square of the cyan layer, and the reflectance of the paper in this case. Yeah. You can also add into this the fact that you have printed barcode. So there is some regions where you have the printing in each color, and you can show that in the density domain, if you have the simple model, you can represent this in the simple model where the reflectance at x, y, and lambda is the reflectance of white multiplied by this term, which is due to the densities over here. Again, in the interest of time, I will not have the time to go into a detailed exposition on printing and so on. But the key idea here is that you're taking into account how much is each of the layers of colorants taking away from light of a given wavelength. So di lambda is giving you the density that each of these, that the ith colorant is contributing at the wavelength lambda xy. Okay. The spatial printing is something which is just a binary pattern. This is what the QR codes are. They're just a binary pattern. So it is not something which depends upon lambda in this case. This is just a binary pattern. Okay. All right. The scanning process will scan this through some camera, such as the camera on your smartphone, which will have some sensitivity. Okay. Those are fairly narrow band, meaning they're concentrated in the red, green, and blue regions, even though they may not be completely monochromatic. We model them as simple monochromatic sensors in our case, and that gives us a rather simple model, which is not linear, but close to linear. If you see this over here, this model is over here. you have this term where things are getting added together in this exponent over here. The di lambda k is the density that the ith colorant contributes to the wavelength lambda k at which the kth channel of my capture device is sensitive. Again, I'll refer you to the paper for the details on this. Otherwise, this will maybe go too long. But it's a very simple model, very similar to the model that you saw in the first part of the talk. Again, we can linearize this by converting to density. In this case, you do not have the difference between the front and the back side that I had in the earlier model, but you can linearize this by converting to density. And in the density domain, this becomes a very simple model, which is a linear model, which is the optical density that you've captured is related to the input images that you printed in the 3 channels by this 3x3 matrix, which is this matrix of densities, which is transforming from what you printed into what you see in the captured image. Okay, this is unknown, and this is what you need to estimate. Okay, this relationship applies in this logarithmic domain. So that's something to keep in mind, that you will have to do some transformations, images which are easy enough in this case. Okay. So how do you do this? How do you estimate this D, which because it changes depending on the illumination, upon what printer you used, and so on? Well, one way to do it is that these pilot blocks that you have over here, these blocks that I talked about, these are used to only localize the QR code and find where the QR code is. They're not carrying any information. So you can change their colors in the color version. And this is what we call pilot blocks. They'll go through the same printing process. So they'll give us information. I know what I want these to be. I know this is green. Since it is, or let me take the simple one. I know this one is magenta. So if I'm looking at cyan, magenta, and yellow, the middle channel is 1 over here. All the other channels are 0. So I know the value of I for these pilot blocks in this case. Similarly, for all these other regions, I know the colors for these. They're not carrying information. These colors I do not know because they depend upon the data that I'm carrying inside these modules over here. Okay. So since I know this, this is something I've measured for the pilot blocks for my captured scan. I can simply do a least squares and get an estimate of what should be the best value of D. Okay. Right. Once I have D, I can take the optical density from the scan channels, multiply by the inverse of this, and get the estimated colorant print channels. And which is this what I can use for my decoding in this case. Okay. Here is an example showing you we did extensive experiments with a number of printers, number of phones. These experiments were done a while back, so you can see the phones are quite old in this case. Okay. The images were captured under typical conditions, which you would expect in typical situations, where the lighting conditions varied. It was indoor, outdoor, fluorescent, and incandescent, and they were captured approximately 15 centimeters from the printed barcode. Okay. How does the technique work? So these are the original print colorant channels that you asked for printing. These are what you captured in the red, green, and blue channels of your captured image. And again, if you remember, the red, yellow channel, this block over here is white inside. This block over here is darker than the block outside over here. So the interference is larger than the primary signal that you see over here. This is a result after the interference cancellation. And you can appreciate that this region interference has been eliminated substantially. All right. How does this perform overall in the barcode? So the overall barcode is quite standard, is quite complex. You can do it for different sizes. You can do it for different levels of error correction and so on. So I will just highlight some results over here for different sizes, as well as the alternative approaches. First, focusing on the yellow channel. If you remember, the yellow channel was the one which had the most interference from the other channels in this case. Okay. These are different techniques for thresholding these codes after you've processed them, which is what is typically done before you decode them. You'll threshold them to get a binary image, which is then decoded. These are the same technique, but without the interference cancellation. This is using our technique of interference cancellation in this case. And what I'm presenting here are the bit error rates. So you can see the bit error rates are quite high, about 20.66%. About 20% of your bits are in error in the absence of any interference cancellation. With the interference cancellation, this goes down very substantially to about 6%. And the error correction coding that you have in these codes can easily correct for the 6%, while it cannot address the 20% error rates that you have. As you go for a slightly larger barcode, this actually goes down. Both of them go down, but these go down to very low values, about 3 to 4% in this case. Okay. So the technique works quite well in enabling this. This is for the magenta channel also, where because the interference is less for the magenta channel, which is what you see over here in these images, the error rates are not that high as what you saw in the yellow channel without interference cancellation, but interference cancellation improves this. Okay. Right. This is the cyan channel where there is very little interference. You can see the error rates are quite low to begin with. Our processing actually increases the error rate a bit, but this is not really significant because this you can easily overcome this with the error correction coding. The error correction coding can readily correct. I mentioned the rates of even 6%. So this error rates of 1% are not that significant. Also, if you know this, you can also try decoding without the interference cancellation upfront. So this is not a fundamental limitation. Okay. Again, interest of time, I'll skip this large table, but we've done extensive experiments comparing alternate techniques, also compared them to monochrome barcodes, and find that the synchronization success rate tends to be very similar. One issue with this is that you have to use these regions, which we call pilot blocks. If you do not want to use these pilot blocks, we can actually use machine learning to estimate this. The simple expectation maximization algorithm is what we can use. And the advantage of that is we do not need to customize design for the barcodes. Okay. Right. Again, I will interest in this. Okay. Right. So what I presented was really a methodology. It's not a method, but a methodology to generalize monochrome barcodes to color. In my results, I only presented the results for the QR codes, but the methodology applies to the other codes also. We did experiments with Aztec codes also, and you can also think of this methodology being applied to the traditional one-dimensional barcodes that I used in the when you each time you go into the store and buy something, there'll be a barcode on it. Key element here is that we're utilizing the built-in components from the monochrome counterpart. We're not redesigning the whole thing. Localization, data encoding, extraction, error recovery is reusing large parts. We've got a 3 times higher data rate that we enable with this. And this can be used in a variety of ways in mobile connectivity to print, maybe for advertisement monetization, multiple other applications. The methodology also generalizes to other barcodes. So this is work we had done earlier, where we were trying to embed an orientation in this case. And we were doing this for color. And to cut a long story short, in this case, we had not quite come up with the interference cancellation approach. We were doing interference management rather than cancellation. Okay. However, after we came up with the interference cancellation approach, we could also use the interference cancellation approach for this and apply it in this setting with the expectation maximization based technique. And you can see our error rate for the yellow channel for this case went down from 28% to about 10% with the proposed technique for interference cancellation. Okay. So these data rates give us quite high rates of information that we can put with the appropriate technology. Okay. Wanted to highlight there's been work done, we've done since then. Originally, when we were working on this, large part of the work on QR codes was printed codes. These days, most applications are using these in displays, and display resolutions have gone higher. They can be used. So this is an example from more recent work showing you these channel-wise barcodes for displays. The methodology tends to be very similar to what I presented for the printed barcodes, except that the physical model is actually simpler. So this is actually a case where things become simple with time. There is lower channel interference, which also allows us to do other things. This is showing you an example of a color QR code embedded in this image. This paper appeared in the Journal of Electronic Imaging, which is one of the journals that SPIE sponsors. Contrast this with the black and white. If you contrast this with the black and white, compared to this, by using the same footprint, we can send 3 times the data. Interestingly, because the channel interference is lower, we can also do something different in this case. If you compare this, so this barcode is much less visible, much less objectionable compared to what you have over here. So that's the idea that your eye is less responsive to spatial detail in the blue channel. So you see this much less. And in this case, we've also chosen this to match the background image. We can do this for the blue or the red channel effectively and make it much less perceptibly visible while still carrying the same information. So the amount of information that you're carrying is the same as the black and white barcode over here, but much less visual distortion in this case. So I listed the references over here. I will not talk about these in any detail. Okay. Much more recent work. We've actually done a combination of some of the ideas I presented earlier. As the screen resolution is increasing, it provides new opportunities. So not only can you make these modules dark and light, but you can also put a spatial pattern over here, which is varying in shape and orientation in this case. So we have the primary message, which is communicated by the barcode. If you decode this with your cell phone, you will find this message in this over here, and this is completely compatible with your normal decoders. However, we also have a secondary message, which is modulated in the orientation of these dots. Each orientation is carrying actually 2 bits of information. There are 4 orientations over here in this case. This is work that has just recently appeared in this case. Right. The kind of applications we imagine for these is that these are particularly good for what we refer to as proximal privacy. You want to communicate information to somebody at a short distance, they can make out not only the global information over here, but also the local orientation of these patterns. So you can decode both the primary and the secondary message over here. From larger distances, you can maybe be able to recover the primary one, but you cannot recover the secondary one. So if you're logging on to a website using your QR code on your displayed smartphone as a way for conveying the information, you are assured that somebody who's a further distance away from you cannot capture an image of that and retrieve this sensitive information in this case. In the interest of time, I will skip this. I guess I had too much enthusiasm in trying to put more things together, but I will just sort of conclude over here my talk by highlighting that signal processing that incorporates physical knowledge offers powerful solutions for a wide variety of problems. And that's the whole theme of this talk. By combining very simple ideas from physics and mathematics, you can actually come up with a whole that is much greater than the sum of the parts. And imaging is a rich source of problems in this class. I illustrated several examples from this. My sampling is obviously biased. I can speak best to my work, but there are many other examples of the work out there. I'd also like to acknowledge the collaborators that I've had over the years that have contributed to different parts of the work that I used over here. So they've contributed to various parts of this work. So with that, I'd like to maybe stop here, and we'll be glad to take questions that people may have.
So there is a question: how many pilot blocks can be made inside a code?
Okay, so there is no fundamental limit to the number of pilot blocks that can be made inside a code, but the limitation is in terms of what regions you can use for the pilot blocks. So maybe this is the idea which is illustrating this. So the key idea here is the regions which I'm showing with mouse. Hopefully everybody can see the regions which I'm marking on by the mouse over here. These regions, with the exception of these large square blocks and the small block over here, they're used for carrying data. So they're really carrying what data you have in your QR code. So that's something you cannot control. Whatever data you choose will determine whether these are black and white. These regions which you're seeing in these different colors over here, the green, cyan, and so on, these are only used for synchronization. They're not carrying any data. So you can use these regions as pilot blocks and change the color as you wish. How many pilot blocks? There is no fundamental constraint, but you're constrained to using only these regions. In the Aztec codes, the synchronization regions are these ones, the ones over here and the block in the center. These are what you could use as pilot blocks. Now, how many of these regions, how you partition them is all up to you. In our case, you can see that's a very simple partitioning. Each geometrically contiguous region is just one block using just one color, but there's no reason you could not split this into two. You could use the upper part over here as one color, the lower part is another color, if you needed to.
Okay. Any other questions or queries? Size of QR code depends on which parameters?
Size of QR code depends on partly how much data you want to communicate. What is the size? Maybe if you're putting a URL, how long that URL is. It also depends upon which of the QR code standards you're using. So there are alternative levels of error correction that you could use. I did not speak to those, but they are there on experiments. So if you look at the experiments, we use alternative versions of error correction over here, which will do this. And then finally, it also depends on your application setting in terms of what distance you want to decode this from. So maybe to illustrate this, if you're imagining this kind of barcode over here, embedded in your image over here, this is something maybe you're watching your TV from a distance. So you're not really, if you're watching this on your TV and this is embedded in the screen on the TV, you're not typically that small distance of few inches away from your TV. You're rarely sort of 9 inches. Nobody's watching the TV from 9 inches these days. Okay. So you'd possibly want to make this bigger, but you can also do that because the distortion this is introducing is smaller. So you can make this bigger. So the size will depend upon these multiple parameters.
Okay, sir. Any other questions? Any other queries? If you want, you can unmute yourself. I think we see a line pattern codes on books back. Which are those codes?
Okay. So those are what are conventionally called the one-dimensional barcodes. That is also a standard. I did not present that here when I'm giving the examples of different codes over here, because I focused particularly on the 2D barcodes, the common 2D barcodes. So the 1D barcodes are used very extensively. They're used for product marking. It's the standard is called the UPC, Universal Product Code. The Universal Product Code specifies how a product gets mapped to the barcode over there, but that's a 1D barcode. Our technique that we presented over here can also be used for 1D barcodes, except that nobody is detecting them with your cell phones. Nobody is sort of, yeah. It's rare that you capture them with a cell phone, though it's becoming more common now as the resolutions have increased for cell phones. But the basic technology will work there also.
So can QR code be printed on any type of materials?
People have explored a lot of different materials for printing QR codes. If you're going to use a printed barcode technique to make it color in this way, obviously the material should be printed on using cyan, magenta, yellow in this case. But yeah, people have printed on many different materials. I think you see these on t-shirts. You've seen examples of these on t-shirts, on packaging. So yeah.
Okay. Any other questions? What is the difference between QR code and barcode?
A QR code is a type of barcode. So what is the difference between animal and cat? A cat is a particular type of animal. So yeah. So that same way, a QR code is a type of barcode. It's a two-dimensional barcode. So rather than the traditional bars you see in the store, which are a one-dimensional barcode, this is what you refer to as, these are all examples of two-dimensional barcodes.
Okay, so do 1D codes have less security?
Security is something which is not in the code itself, but depends upon the way you use the code and in the protocol in which you use the code. So as they're designed for applications for product labeling, security is not the key objective. The key objective is to convey the information in a manner such that you can manage your inventory much more easily. So if a store owner is doing a checkout, if they had to pick each item by name and pick them out and then pick up the price, that would be a lot of time that would be quite time consuming. Whereas by scanning the barcode, they can quickly recognize what item this is. So it's more used for identification. The primary application is not on security. Okay. However, you can use them for security with appropriate augmentation and protocols. So that's, for instance, the dual modulated QR codes. That was motivated by a security application, and that's one we will, yeah, if you can look at how that is used in security.
Okay. Can a QR code have errors?
Yes, a QR code can have errors. There are both errors which are sort of inadvertent errors, just from the capture process or the printing process. There may be errors which may be introduced. Also, you would have commonly seen these. People will put a logo on top of the QR code somewhere. So they'll use a certain region of this to put a logo. And that logo will introduce an error in the data, which your decoder has to correct for. So you're actually relying on the error correction capabilities of the decoder to correct for the errors that you may be introducing by introducing a logo in a certain part of the region over here.
Okay, sir. Any other questions or queries? What is the difference between static and dynamic QR codes?
What is the difference between static and dynamic QR codes? So I'm guessing so I don't exactly know. I have not encountered the term dynamic QR codes. My guess is that dynamic QR codes would probably be something on your smartphone, which you're dealing with. So a static QR code would be one which is like the one you see over here. The pattern is fixed. What data is encoding is fixed. A dynamic QR code is probably one which you're using probably for point of pay systems. So if you're paying somebody by showing a QR code. So when I travel to China, almost all payments in China are handled by QR codes. So even the beggars on the streets will have a printed QR code which you can scan on your smartphone to give them money. They will not have, nobody handles cash. Okay, and literally, it's even the beggars on the street will be using these printed QR codes as a way to get this. Okay, so an example of static QR code is where the information is not changing, but when you're paying somebody with a QR code displayed on your screen, the information is changing depending on how much you're paying them, and you also don't want somebody able to reuse that. So that would be something which would use a dynamic QR code. So that's my guess.
Okay, so is there anything like 3D QR codes?
Is there anything like 3D QR codes? So I think we've seen some people mention 3D QR codes. The number of versions of these have corresponded really just to color QR codes. So some people have called these color QR codes as 3D QR codes because these are two-dimensional, and adding the dimension of color, they call these 3D in some case. That's not really completely accurate. I would not really call them 3D QR codes. So in the strict sense, there's not really anything which I would call a 3D QR code at this moment. However, some people have referred to color versions as 3D versions of the QR code.
Okay, so any other questions or queries? What if there are holographic QR codes? Will it be more efficient like in the future when Google lenses will be more popular?
Okay, if there are holographic QR codes, it's a good idea. I don't know, and I can't say for sure. So that's an idea for you to explore and possibly come up with new designs and technologies.
Okay, sir. Any other questions? So I think there are no more questions.
Okay.
Sakshi, you can continue.
So should I stop sharing? Should I stop sharing?
Yes, sir.
Actually, I guess I've stopped sharing anyway. Okay, please go ahead.
Thanks, sir. The secret of getting ahead is getting started. Thank you, sir, for this enlightening and entertaining session, for sharing your knowledge and experience with all of us. Thank you for accepting our invitation and proffering your precious time. We all are inspired by your words of wisdom. It was a pleasure having you with all of us. We owe you a special vote of thanks for being here. For the same, I would like to invite Dr. Amit Garg for presenting the vote of thanks.
Thank you, Sakshi. My big sincere thanks to you, Dr. Gaurav. Such a difficult topic you have explained in such simple language. Means all these things are so difficult to understand, but the way you have presented them, it has really made them understandable at this particular level, because it is easy to talk of research, but to make that research understandable to a UG audience is really a challenge. And I would like to congratulate you for successfully communicating this particular thing, this particular technology technique to our UG students. So that was really a very interesting talk. Means you could understand each and every step as you moved along, just bypassing the difficult, complex mathematical part, relating it with the basic physics. So it was really, really very interesting. Secondly, the most important part which you highlighted and our students should understand is that whenever you are developing a particular technology in the form of a product, so look at the work which is being done at the development level. So Dr. Sharma has shown you so many data. Means whenever you are developing a QR code, you just see a QR code and just put your mobile phone in front of it. But look at how this technology has been developed. So you are scanning that particular QR code with you can say low resolution mobile phone, still you are getting it correctly. You are scanning it with a good phone, you are getting it correctly. You are scanning it in different ambient light conditions, still you are getting it correctly. So look at how technologists basically work on a particular problem. So you people should also understand this, that technology development in the form of a product is a big challenge. You can develop small prototypes that may work for you can say something, and they may not work for some other thing. But once you develop the technology, as Dr. Sharma has shown us wide his experience at the industry, such a wide experience at the industry, and right combination of academics and industry. So your students must have been really been benefited when this two things go together in your teaching. So thank you very much. It was really a very interesting and enjoyable talk. I enjoyed it completely. So with these words, I would like to express my sincere gratitude to you for sparing your time and addressing the students of University of Delhi at ANDC SPIE student chapter. So we really owe this from you. So thanks a lot.
Thank you.
Yeah.
Thank you so much, Dr. Amit. It was my pleasure. And thank you for organizing this, and for everybody for the engagement and questions. For the younger students, I would also say there's also a message in this talk about being sort of productive in what you're doing and thinking about creative ways in which you can use. As I mentioned, the first example was an example of something which I used, information which I learned in my summer internship as an undergraduate, way back as an undergraduate, and I could use that for an actual research problem. So don't think that what you're doing will not be useful. If you work in research and technology, you do not know ways in which you will find connections and how things will become useful later in life.
So thank you so much. We look forward to some more talks from you in future. So we'll be in touch.
Hopefully sometime when in Delhi, hopefully we'll get a chance to do it in person.
Yeah, it will be the greatest pleasure for us because this COVID has really tightened every one of us to our homes only. So we hope this situation relents and we are out of our homes interacting physically with each other. So it will be a great pleasure. So whenever you come to Delhi, so please call us and we'll not miss this opportunity of interacting with you. Thank you so much. Thanks a lot.
So you have a good rest of the evening, everybody.
Yeah, thank you so much.
Bye.
Thank you so much, sir.
You're welcome.
Thank you,
You're
sir.
welcome. You're welcome. Bye.
On the behalf of our entire SPIE family, I would like to thank each one of you for joining us today and being a patient listener. Thanks a lot, sir, for joining us today. We surely earned a lot of new things today. Thank you once again.
You're welcome.
Thank you. Bye-bye. Namaskar.
You may all leave now.